Yeah. Hello everyone. I welcome you to this session on experiment on Young's modulus of elasticity, finding out the Young's modulus of elasticity E for copper. I am assisted by my colleague Professor Tushar Howard in explaining this, conducting this experiment, recording this video and uploading it onto the net. We have already discussed this in detail in our session, previous session. Nevertheless, I will be conducting the experiment once more here for the benefit of all those who missed the class. Okay, and then the way in which the experiment could be conducted, how to note down the readings, and what are the calculations. So this is my plan for today's session. I will also be conducting one more experiment later on calibration of thermocouple. We will conduct it in a separate video. We will record it separately. Okay. Now I'll take you to the first part, that is calculation of Young's modulus of elasticity for copper. This is dated 2nd/11/2020. It was M lab, in which this comes under measurement section. This is the tabulation. These are the given things for our lab or the experiment, that is length of the beam 15.5 centimeter, breadth 2.53 centimeter, thickness T as 0.342 centimeter. Okay. The initial set of calculation is here to find out the section modulus. For a rectangular beam, the section modulus is given by BT square by 6. No matter what the experimental setup is, this will remain the same. Okay. So the breadth B is 2.53, T is 0.342 square and divided by 6. This answer comes out to be 0.046931 centimeter cube, cubic centimeter. And this is the tabulation. I'll explain the experimentation, no doubt, but prior hand, let us keep the tabulation ready so that we can continue with our experiment. Okay. The tabulation consists of main 4 or 5, 6 columns, serial number, load. This is known to us, 0.2 kg, 0.4 kg, 0.6 kg. These are the loads that we are going to apply. Next, moment. This is bending moment, which is nothing but force into length, F into L, where F is in kgs, length is in centimeter, F into L. So we can say this as kg centimeter. I have already mentioned here. So let us be very specific, kg centimeter. Okay. So I have already calculated this, 0.2 into 15.5, 0.4 into 15.5, 0.6 into 15.5. Effectively the answers are 3.1, 6.2, 9.3 kg centimeter. Okay. Next, stress could be found out by using stress is equal to M by Z. M is 3.1. Z we have already found out. Please note, section modulus is denoted as Z. Okay. So Z is known. Answer is 3.1 kg centimeter. This is stress. Okay. Strain is 0.04931 cubic centimeter. So 1 centimeter and another centimeter getting cancelled. You get answer in kg per centimeter square. Answer here, first question, the serial number 1 for 0.2 kg. Stress is 62.867 kg per centimeter square. Okay. So the stress for the first set of reading is 62.867. In my previous session, I have already explained and given you the answers for 0.4 and 0.6. So I have left these cells intentionally blank. I request you to fill these blanks. Answers have been supplied, but you can do it by yourself. 0.4 divided by this much, 0.6 divided by this much, and find out the answer, write it here. And next comes the strain. These are the strain values which were supplied yesterday, and I am going to show now how to get the strain values. The strain values are received from our experimental setup. Okay. The experimental setup, the strain values for 0.2 is around 214, 0.4 it was around 510, 0.6 around 775. Let's see how much we are going to get now. Okay. But for your calculation purpose, you please do these, note down these values and calculate the Young's modulus of elasticity. And obviously the last section is, and please note, indicated reading of strain is these numbers, 214, 510, 7.5. But for epsilon, you need to divide E by 4, noted value E by 4 multiplied by 10 to the power 6 minus 6. Then same thing I have mentioned, 214 divided by 4 into 10 to the power minus 6, 510 by 4 into 10 to the power minus 6, 775 by 4 into 10 to the power minus 6. Next, Young's modulus of elasticity for copper, E for copper. I repeat, E for copper is stress by strain. And we have found out the stress, we have found out the strain. All you need to do is stress divided by strain. Answer comes out in the first value as for 0.2 kg, it is 1.17 into 10 to the power 6 kg per centimeter square. This is in the denominator you get 10 to the power minus 6. When you take it to the numerator, transfer it to the numerator, you get 10 to the power 6 plus 6. So the answer is 1.17 into 10 to the power 6 kg per centimeter square. I hope I'm very clear about it. Next, do the same calculations here as well and for this as well. And please note, the Young's modulus of elasticity is nothing to do with the load. It will not change with the load. It is a constant, right? Young's modulus of elasticity within proportionality limit is a constant. So we get three values here. Find out the average value of that and write down the average Young's modulus, which comes in the range of 0.9 or 1 or 1.1. In this range, 0.9 to 1.1 into 10 to the power 6 kg per centimeter square is the answer that you are going to get. Okay, one or two or three conclusions is that we have conducted the experiment on Young's modulus of elasticity. Then the value of Young's modulus, average Young's modulus was found out to be, say, let us say 1.1. 1.1 into 10 to the power 6 kg per centimeter square. Third conclusion is that this standard value of Young's modulus E for copper is around 1.1 kg per 1.1 into 10 to the power 6 kg per centimeter square. Our experimental value is favorably comparable with that of theoretical or the standard value. Now let me take you to the experimental setup. Please, you can come this side. Okay, and let us get going with the experimental setup. This is the setup that we have. Let me first show you the main setup. So this is the digital strain indicator. This is the load where this is the loading pan. We are going to apply the load here. Next, this is the beam on which the values are mentioned: length, breadth, and thickness. You don't have to by heart these values. It is already mentioned and is given in your specifications. Okay, and question comes again, like in our previous experiment we had done on load cell. Where are the strain gauges mounted? There are 4 strain gauges mounted here, 2 on the top surface and 2 on the bottom surface. For that, you have a look at this. These are the strain gauges, 2 strain gauges, extremely thin wire. You know, they are electrical resistances, extremely thin. They are thinner than our hairs, I must say. Okay, they are in micron level, sub-micron level. 2 are on the top surface, another 2 will be here on the bottom surface. They are located here. And these are the 4 wires of the Wheatstone's bridge circuit. 1, 2, 3, 4 wires. Similarly, we have this is for steel frame. This is Young's modulus of elasticity for steel. This is the steel bar and this is the copper bar. This is the copper bar, right? So, okay. So, this is the copper bar. We are going to apply the load here and this load will exert the bending here. The maximum bending moment occurs somewhere here and that is where we are going to place the strain gauges, digital strain gauges. Okay. With this setup, now let me showcase the readings with adjustments for the load indicator. Please note the gain factor for load indicator is 400. You need to adjust the gain factor using this knob. So this one entire rotation of knob will change the value by 100 gain. So here we want to fix it to it's 400 gain 4. So we need to fix it to 400. Now these are values indicated on the vernier caliper here. Vernier scale is 0, main scale is 4, so that means this is 400. Okay, and set these values to 00. Set the values using coarse value and coarse setting and fine setting to 00. Okay, I have set this to 00 as much as possible. Okay, this much error is acceptable. Okay. This keeps fluctuating because of our electrical fluctuations and other disturbances that we have. Okay, now with this, and one more important setup is 4-arm and 2-arm. As you can see the knob here, there is a switch for 4-arm and 2-arm. We are keeping it to 4-arm position. Why? Because this is the 4 arms of a Wheatstone's bridge. Can you see? R1, R2, R3 and R4. Okay, with this Let us get going with the conduct of the experiment. Please note, this is the copper bar. We are trying to find out the Young's modulus of elasticity for copper. Okay. Now let me apply 200 grams. For 200 grams load, as on now, the value shown here is 267. And the value I have shown, or yesterday I have given you the value in my readings as 214. Please note 214. So it keeps varying depending on the condition. Now it is showing 264. You can note down even this as well, 264. I have done the calculation for 214. If you can see the previous table that was shown, it is 214. Next, for 400 grams, the digital strain indicator shows 530, 500, it is varying between 535 to 540. So let us say 540. I have given you 510. The reading that I have given is 510. Okay. Next, for 600 grams, the value here is, now it is showing around 792 or 798 or 800. Yeah, 788, 89. These are the readings that it is being shown. I have given you the reading as 775. Please note the reading 775. So freeze these three readings. For 0.2 it is 214, 0.4 it is 510, and for 0.6 it is 775. Once the readings are noted down, that's all is the experiment here. It's over. Rest of the thing remains is what you need to do is find out LBT, find out section modulus, then find out the moment, find out the stress, find the strain. Strain is 200. These are the strain indicated values. But then you need to find out E by 4 into 10 to the power minus 6. Once these three values are found out, calculate E for copper, E1, E2, E3. Three setups. You can even continue further for fourth reading. And then note down the average value of Young's modulus of elasticity. This completes the experiment on finding out or in the determination of Young's modulus of elasticity for copper. You could be given Young's modulus for steel, so don't by heart the readings. It is 2.1. For my Young's modulus of elasticity for steel would be 2.1 into 10 to the power 6 kg per centimeter square. So you will be getting different answers altogether, right? So this we should bear in mind. These are not the only readings. Readings could differ. So you should be very sure whether you are given with for copper or for steel, mild steel. What is the experiment? And this knowledge we can use it for finding out Young's modulus for any other value, any other material in the industrial circle. Thank you.